In this next online lecture, I'm going to talk a bit about when rotation is important. So that is, when does the rotation of a reference frame become significant and how it modifies the physics. If you're going to think about the pseudo forces that are introduced by making some observations in a rotating reference frame, we're going to think about what kind of rotation is significant and causes a significant pseudo force compared to the regular forces in the problem. So we could think of this as when rotation matters. That's the main topic here. And the reason I was thinking about this is because if you do a problem where and you'll do some of these in your homework problem where you've got some rotating system and you need to calculate the centrifugal forces and the Coriolis forces. These are the pseudo forces that come about from rotation, as you'll see in the next lecture. Then when you're computing this, we always ignore the fact that this is some problem that may be sitting on the surface of the Earth. The Earth itself is rotating, right? And the Earth is not only rotating about its own axis, it's also orbiting about the Sun. So there's another type of rotation. Not only that, the Sun is orbiting around the center of the galaxy. So you've got all these different rotations all going on simultaneously, and we generally ignore all of them. So I'm going to show you in this short lecture that this is sort of a valid thing to do. Okay, so remember from last time we showed that this is the basic result we showed from last time, that if we want to know what's the time derivative of some vector in a rotating reference frame, then that is equal to the time derivative in the stationary frame modified by this omega cross v term. So if this term is small, or is sufficiently small, then the time derivatives of two vectors are essentially the same in the two different reference frames. So in other words, if this is small enough, we can neglect it and say that the physics and the equations of motion and everything will be the same, roughly, in the two reference frames. So let's think about that. So the magnitude of this thing, the order of magnitude of this is, it's related to omega and whatever vector you're talking about. So let's consider omega for the rotation of the Earth compared to some typical problem that you might do. Okay, so let's put as a baseline. Okay, so for some sort of typical textbook problem on these rotating systems, typical problem might be something like if you considered a turntable or a record player. So a record player rotates at, say, 33.5 RPM. Oops, RP, rotations per minute, right? So this corresponds to the magnitude of omega here is something like 2 pi radians per 60 seconds, roughly. So this thing is equal to about 0.1 radians per second, approximately. Okay, so this is, for example, the kind of rotation rate that may be causing a modification to the time vectors, the time rate of change of vectors that we're doing in a problem. So let's see how this compares to the rotation rate that is also going on due to this record player sitting on the surface of Earth, right? Okay, so for Earth rotating about its own axis, the period for that motion is 1 day, right? So for that, let's say let's call this omega naught, and we'll call this omega 1. So this one it does 2 pi radians in 24 times 3600. So this is the period of this has period 24 hours, right? And 3600 seconds per hour. So it does 2 pi rotations per this many seconds, 24 times 3600 seconds. So this thing is 7.3 times 10 to the minus 5 radians per second. Right? So the point here being that this is quite a bit smaller, about 10,000 times smaller than the rotation vector due to a record player. And this is in spite of the fact that, I mean, I think intuitively you might think that the rotation around the Earth is somehow more intense because we're flying around, right? You know, the tangential speed, maybe we could write that down over here. So something like the tangential speed of us as we move around the Earth, as it rotates, is, well, that is omega times the radius of the Earth, which is something like 460 meters per second. You have to take my word on that. The radius of the Earth being 6.4 times 10 to the 6 meters. So even though we're flying around much faster than a record player is moving, the important thing here is that the rotation rate in radians per second is much, much smaller. That's the only thing that plays a role in this modification due to rotating reference frames. Okay, so what about for the Earth orbit around the Sun? In that case, let's call this omega 2. We have, it does 2 pi radians, that's 1 full orbit in 24 hours times 3600 seconds per hour times 365 days, right? That's how many seconds it takes to do 1 full orbit around the Sun. So that thing comes out to be 2 times 10 to the minus 7 radians per second. So you can see that as long as this orbital, or this period of the rotation is getting bigger and bigger, this omega is going to get smaller and smaller. So we went down by another factor of 100 compared to the omega due to rotation about the Earth's axis. Similarly, for the solar system orbiting around the galaxy, the center of the galaxy, in that case, let's say omega 3, we get something that's, well, the orbital period for that motion is 2.3 times 10 to the 8 years. So this case is going to give us something on the order of 10 to the minus 15 radians per second. So the point being that if we're going to do a problem that has rotation involved, say like this record player, that we can completely neglect the other sources of rotation in the universe in our particular rotating reference frame, right? We are in a rotating reference frame. We're on the Earth that's rotating about its own axis. It's orbiting around the Sun. The Sun is orbiting around the galactic center. But those sources of rotation are such small corrections to omega that we can neglect them. So that's the point here.